Ever pondered what is language in the theory of automata and why is it important? Well, you're about to find out. In the realm of theoretical computer science, the concept of language is paramount, especially when delving into the theory of automata. Now, when we refer to language in this context, we're not talking about spoken or written languages like English, Spanish, or Mandarin. Instead, we are referring to a set of strings derived from a specific alphabet. Sounds intriguing, doesn't it? Let's get a bit more technical for a moment. Formally, a language, symbolized as L over an alphabet sigma, is a subset of the set of all possible strings formed from symbols in sigma. This concept is absolutely crucial in computer science, particularly when it comes to understanding the capabilities and limitations of computational models. Now you might be wondering, what's an alphabet in this context? Well, it's not quite ABCs. In the theory of automata, the alphabet, represented as sigma, is a finite set of symbols used to construct strings. For instance, if your alphabet is 01, then your strings could be something like 101 inches or 1101. And what about these strings we're constructing? A string over an alphabet sigma is simply a finite sequence of symbols selected from sigma. So, if your alphabet is 01, 101 inches is indeed a string over sigma. Now, when we talk about a language over an alphabet sigma, we're referring to the set of strings that can be formed from symbols in sigma. It's important to note that a language can be either finite or infinite, depending on the number of strings it contains. This is just the tip of the iceberg when it comes to language in the theory of automata. There are many other key terms and concepts to unpack, such as regular languages, context-free languages, and recursively enumerable languages, each with their own unique properties and significance. Now, let's dive deeper and explore some key terms and concepts related to languages in the theory of automata. The first thing to understand is the alphabet. In the realm of automata theory, the alphabet isn't a list of 26 letters. Rather, it's a finite set of symbols from which strings are built. In simpler terms, an alphabet is like the building blocks you used as a child. Each block or symbol can be used alone or combined with others to create something bigger. In this case, a string. An example would be the binary system, where the alphabet, designated as sigma, consists of just two symbols, 0 and 1. This might seem limiting at first, but remember, it's the combination of these symbols that creates complexity. A string could be as simple as 0 or as complex as 01101. Remember, the alphabet is the foundation, the starting point. Without it, there would be no strings, no language. So an alphabet is just a finite set of symbols from which strings are constructed. Next, we have strings. In the realm of automata theory, a string is a concept that's as simple as it sounds. Picture a strand of beads, each bead representing a symbol from the alphabet. This strand or sequence of symbols is what we call a string. Now let's consider an alphabet, say sigma equals 0, 1. This is a binary alphabet consisting of just two symbols, 0 and 1. If we were to create a string using this alphabet, it might look something like this. 101. This string is a finite sequence of three symbols, chosen from our binary alphabet. It's important to note that strings are finite. They have a clear start and end, much like the strand of beads we visualized earlier. When we talk about strings in automata theory, we're usually interested in how they can be manipulated, patterned, or recognized by different types of automata. So, a string is just a finite sequence of symbols chosen from the alphabet. Now, let's talk about the concept of language. In the theory of automata, a language is a collection of strings over a given alphabet. You can think of it as a set of sentences, each sentence being a string formed from symbols in the alphabet. A language could be either finite or infinite, and this is determined by the number of strings it contains. To help you understand this, let's consider a couple of examples. Imagine we have an alphabet, sigma, consisting of the symbols 0 and 1. If we define our language L to contain all strings of length 2, we would have 4 strings, 0, 0, 0, 1, 10, and 11. This is a finite language because it contains a finite number of strings, precisely 4. On the other hand, if we define our language L to contain all strings of any length, we would have an infinite number of strings. Why infinite? Because there's no limit to how long a string can be. You can always add another symbol to any string and create a new longer string. So this language is infinite. It's also worth noting that a language doesn't have to contain every possible string over its alphabet. It's a subset of the set of all possible strings, which means it could include some strings and exclude others. For example, a language over the alphabet, 0, 1, might only contain strings that start with a 1, or strings that contain an equal number of 0s and 1s. The rules that determine which strings belong to the language are defined by the grammar of the language. In the context of automata theory, languages are used to describe the sets of strings that various types of automata can accept or recognize. They help us understand the capabilities and limitations of different computational models, and they provide a theoretical foundation for many fields, including computer science, linguistics, and mathematics. So, a language is a set of strings formed from symbols in the alphabet. There are different types of languages in the theory of automata. Let's start with regular languages. Regular languages have a particular charm because they can be recognized by a finite automaton. Picture a traffic light system, where changes depend on the current state and the input. That's how a finite automaton operates. Regular languages are also closed under operations such as union, concatenation, and the clean star, a fancy term for repetition. A classic example of a regular language is the set of all binary strings ending with a 1. Next, we have context-free languages. These languages can be generated by a context-free grammar or recognized by a push-down automaton, which is like a finite automaton but with an extra feature, a stack that allows it to remember an unlimited amount of information. Context-free languages are crucial in parsing, a process that interprets a string of symbols in a systematic way. An example, the set of all balanced parentheses strings. Now onto context-sensitive languages. This type can be generated by a context-sensitive grammar or recognized by a linear bounded automaton. These languages are more powerful than context-free languages, but not quite as powerful as the recursively enumerable languages. A context-sensitive language example would be the set of all strings of the form a circumflex NB circumflex NC circumflex N, where N is greater than or equal to 1. Lastly, we have recursively enumerable languages. These languages are the most powerful in the hierarchy we're discussing. They can be recognized by a Turing machine, a theoretical device that manipulates symbols and can simulate the logic of any computer algorithm. Any language that a computer can recognize is a recursively enumerable language. For example, the set of all strings over the alphabet of 0 and 1 that represent the encoding of a Turing machine which halts when run with an empty input tape. Each of these language types is unique, and they're crucial in the theory of automata. They describe the sets of strings that different types of automata can accept or recognize. They also provide a theoretical foundation for understanding the capabilities and limitations of computational models. So, these are the different types of languages in the theory of automata, each with its own unique characteristics and importance. Now, you should have a basic understanding of what language is in the theory of automata. We've delved into the alphabet, which is the finite set of symbols we use to construct strings. From there, we've explored how these strings come together to form languages, which can be finite or infinite, depending on the number of strings they contain. We've also discussed the various types of languages, such as regular, context-free, context-sensitive, and recursively enumerable languages, each with their unique characteristics and recognizable by different types of automata. It's crucial to remember that these concepts are not just academic exercises. They form the foundation of formal language theory, automata theory, and computational complexity theory. They help us understand the capabilities and limitations of different computational models, which is invaluable in the field of computer science. Remember, understanding the concept of language in the theory of automata is a stepping stone towards mastering the field of computer science. Keep learning.